Hello, so I'm Wei Song, a research associate from University of Cambridge, working for low risk. And quite happy today to talk about our second code release, which will provide an untethered rocket chip. That means right now you can boot a RISC-V Linux from the rocket chip using an FPGA board without the help of the ARM core. So a little bit introduction about low risk and RISC-V. The rocket chip is an open source SoC developed from Berkeley. And the rocket chip chose to use the rocket core, which is running the RISC-V 64-bit ISA. And it's 5 to 6 stages, one issue in order core. And for low risk, we are kind of open SoC provider, hope to provide some open source SoC solutions for companies. Here in this slide shows the original rocket chip structure. So you can see it has one to many rocket cores. Every core has its own L1 cache. And there's a banked L2 cache connected to those cores, and the banked L2 is connected to memory. The memory system is all there, but something missing is about I/O devices. So the original rocket chip need to use a host target interface and plus a ARM core to access the I/O devices actually located on the ARM side. Also, because there's an ARM core, so the original rocket chip doesn't need anything related to bootload. The ARM core will handling all the bootload process that kind of copy the Linux kernel from SD card to the memory, etc. And if the rocket chip want to use some I/O devices, basically it will send out messages through the host target interface and let ARM do all the rest. But for our purpose, we want to have a standalone system, which you don't need the ARM core to handle everything. We want the rocket chip to bootload itself and run a RISC-V Linux without help from ARM. So that's why we propose this structure. As you can see, that we have replaced the ARM core with the real I/O devices. Currently, is provided by Xilinx IPs. We utilize the FPGA block RAM as the initial boot RAM, and also connect to DDR3, which is on board. For the I/O devices, currently we only have a UART, which will give you a terminal. Another thing is SD card, so you can put your, currently we put our second stage bootloader and the Linux kernel onto the SD card. So all of these things will be copied to DDR memory later. Also for the rocket core to talk to I/O devices, we need support from memory mapped I/O. We add memory I/O support in the current L1D cache and add another separate tail link to directly talk with I/O devices. So that means the I/O read and write are totally uncached. And one thing we think important is we kind of encapsulate all the Chisel part into a Chisel island. So the top level actually is in system Verilog. All the I/O devices and on-chip interconnection are implemented in system Verilog. The Chisel island has the rocket chip. Currently only have 2 interfaces to the top level system Verilog. Those are a nasty interface and nasty light. For the people who don't know nasty, actually it's implement a subset function of AXI. So currently we do have AXI and AXI Lite support. Well, not for standard. Right, partially due to the boot process, I need to add some I/O and memory maps here to allow me to define which memory space is actually uncached and which memory space is cached. Also allow me to readdress some memory sections to another address at runtime. So there are up to 4 I/O sections. It's totally defined at runtime. You can enable or disable certain memory addresses and define them as I/O addresses. And for the memory, also up to 4 memory sections. Some special for the memory section is that actually you can redirect a memory section to another address. For example, the DDR3 is actually on a high address. I can later define that to the address 0 to make it a boot path. So any address if get a hit in the I/O map, that means it's uncached, considered as I/O. So also I can map DDR3 into the I/O section to bypass cache. For the memory map I/O, I add load support in the L1D cache. I know currently the RISC-V Rocket Core also support memory map I/O, but we kind of start at around the same time. We end up in different designs. I will look what happened in RISC-V and merge it later maybe. Right now, for any address that get hit in the I/O address, I suppose it will be missed in the L1D cache. And there's an I/O map here, will generate a hit, say this address actually is I/O address. Then another added I/O missing handler will handle this I/O request, actually send out the request using the separate tail link to the real I/O devices. If there's a read, then the I/O missing handler will get the data. Then feedback data use the same replay process in the L1D cache. So kind of 2 or 3 o'clock later, the processor will get the data from the I/O devices. And because I only have one I/O missing handler, so all the I/O read and write are kind of in program order and have no side effect. Make sure they kind of in sequence and totally uncached. Okay, right now I can talk about how the RISC-V Linux can be booted on this structure. I use 2-stage bootloaders. The first state bootloader actually will read the second state bootloader from SD and copy it to the DDR3. The second state bootloader needs a clean reset. That means the first state bootloader needs to copy the second state bootloader, bypass the cache. As after reset, any data in the cache will be lost. So the first state bootloader will first map the SD card memory space and the DDR3 memory space or to I/O space. So that means the whole copy is actually bypass the cache. Make sure all the second state bootloader will be copied to DDR3. Then the first state bootloader will change the address map, mapping the DDR3 to address 0, so the second state bootloader can get a clean boot. After soft reset, the second state bootloader will try to load the Linux. Actually, the second state bootloader is a revised Berkeley bootloader. What it do, it will first initiate the virtual memory, at the same time enable all the I/O devices, and then copy the Linux kernel from SD to the virtual space. After that, it will boot the Linux kernel directly from virtual space. And during the Linux kernel running, the second state bootloader kind of, I think, is running as a hypervisor to serve the I/O devices. So if the Linux kernel want to access to I/O devices, I believe they send out requests through system cores defined as SPIs. The revised Berkeley bootloader will intercept this request, translate it, and serve it with the real I/O devices, generate response sent to Linux kernel, kind of handle it. So Linux kernel still believe it's talking with a host TAC interface, but actually it's served by the real I/O devices. Okay, so for this code release, we have we prepare a kind of extended tutorial, explain everything, so you can read it from our website. And all the code are released from GitHub, where you can download right now. There are some key features in this release. The first one is we support 2 FPGA boards. The first one is a Kintex 7 KC705. It's a high-end FPGA board which we use in a developing system. The other one is we support a low-end FPGA board, the Nexus 4 DDR board, which you can buy it for kind of a little bit more than 200 quid. Both boards can boot the RISC-V Linux. So right now, it's quite easy to boot RISC-V on any FPGA board. And we kind of merged the up-to-date Rocket Core from Berkeley, at least up to the end of October. And one important change is that we have get rid of the VCS and replace it with Varilator, which is free open source tool. That means right now, as long as you have PC running the Ubuntu and has an FPGA board, there's no other cost for you to run the RISC-V Linux or debugging, doing any development you want. Here are a summary of other changes. So we have removed the host TAC interface and add 2 maps, I/O map and memory map, and add a memory map I/O supporting the L1D cache. We have totally rewrite the tail link and nasty interfaces to be compatible with the Xilinx XI interfaces. We also provide on-chip nasty interconnect, which has this kind of equivalent function of the XI interconnects provided by Xilinx, but currently our version is totally open source and free. We have integrated DDR2 and DDR3 controller for the two board, and add SD card which can support FAT32 and add UART for the terminal. We use two-stage bootloaders, and the new environment is totally free. Of course, we provide a whole makefile and a script, therefore you can see how we do it, and you can make some changes. There are two missions in this release. One thing is we don't support tag memory right now. We intend to add it back quite soon, and we probably won't go into support that board in the near future. So for the future work, well, kind of relate to me. I'm not totally sure about the SPIO system cores from current Linux kernel, and I'm a kind of hardware guy. So if that thing is going to be specified by this platform spec or get to be removed, I hope I can get some help from people who understand Linux kernel to remove the host tag interface currently reside in the Linux kernel. And I'm going to reintegrate the tag memory. And one important thing is to add an interrupt controller. Right now, the interrupt is hooked up with CSRs I defined as kind of ad hoc. I probably hope there's a proper interrupt controller to be a start point. And we are going to add trace debugger with help from Stefan. Also, I noticed like Sci5 is going to define the debugging spec, which including some trace. We will look at that and see how we can integrate trace for that spec as well. Also, we are hoping to add run control debugger after the release of Sci5. And one important is we need to see what happened for the platform spec, because right now I just get all the things done as soon as possible, so all the things are defined by me and probably not proper. Right, for all the information you want, you can get them from the RISC website and see. That's all, thank you.
Great, thank you, Wei. So questions for Wei?
Hi, I'm Mark Beal from Intrinsics. The Verilator support, I was interested in that. Did you have to change anything in the way the Chisel output works or anything in your system for the language compatibility with Verilator?
Verilator has some problem with the printf, so I add some patch to change the code generated by Chisel, but nothing has been changed to Verilator.